So we're going to continue our discussion in section 3.1 by looking at other bases. Specifically, we had left off last time having talked about base 10. Get there just a sec. Base 10 blocks. And we had quickly looked at what happens when we were in base 8 and talked about that if we were a Flood Flintstone, we'd have base 8. I mean, that's probably what we would be operating in, right? So we're going to take a look at 3 other base systems. Again, this is sort of arbitrary. There's nothing special about these base numbers. We're just using 3 of them. The first one's going to be base 3. Oh, before I do this, let me make one mention. So a couple things that I was thinking of as I was planning to come and discuss this with you today is, number one, we use other bases in real life. They are used. Do you know of any places where other bases are used, where we count in a way that's not counting by tens? Can you think of any? Time is the primary one that we utilize on a regular basis, right? So our clock's in 12, but if you do minutes, they're in 60s. Minutes and seconds are in 60s. So we have this sort of odd base 60 system almost with our minutes and our seconds. But then we've got a 12 or 24 if we're doing it for time system that we use, and we repeat and we start over again on our numbers when we do that. So time is a really good one. What's that? Measurement sometimes too. So think about inches, right? Feet and inches, right? We've got the 12 going on there as well. So that's another one. Can you think of any others? Maybe they're not used in your life specifically, but they are used. Can you think of one, Chesney?
Well, I don't know if it really counts, but we count by 8 when we dance.
Okay, so music. In music, and music does it in quarters too, right? A lot of times you do things in fourths, in 4 beats in a music. So that's another good example. I've never heard anyone mention that before, but you're exactly right. Yeah, that would count. Yeah. So I know computer science is probably not y'all's, number one thing because you're not in a computer science class. But our computers are coded in binary. Binary is zeros and ones. There's only 2 digits. We're going to talk more about the digits in these systems. So everything's coded that way. Or computers are also sometimes coded in hexadecimal. Hex 6, hexadecimal 16. It's base 16. So we do have other bases that are utilized like real life kind of stuff. Part of the reason, though, that we're doing this is not necessarily for that reason, in the sense that it's a very practical purpose kind of thing. But this section is going to make you feel a little bit uncomfortable. And sometimes it's good to feel uncomfortable with material that we've gotten very comfortable with. Because we're about to start in section 3.2 with addition and subtraction of whole numbers. You're very comfortable with that, right? You're very comfortable with that. And sometimes it's good to put on the hat of what our students feel like when they're first encountering things that for us have become very comfortable again. And so part of this section's goal really is to make you feel a little bit uncomfortable. So if you do feel a little bit uncomfortable, it's okay. All right. All right, so let's look at these 3 base systems that are up here. Base 3 is our first one. So if you think about our base 10 system, our base 10 system starts at 0, and it goes to 9, and then we increase to 2 digits, right? So there's not actually a single digit in base 10 that's a 10. Right, it's a 2-digit number. The number 10 in our system is a 2-digit number. Everybody with me on that? Okay, so there's no 10 as a single-digit number in base 10. There's only the numbers 0 through 9. The same thing's going to happen when we work with other bases. If we're in base 3, there's not going to be a 3. If we were in base 8, that's the one I did last time, there's not going to be a base 8. There's not going to be a number 8. Okay? So what does it look like for us to have base 3? Well, it means we're going to have 3 numbers, right? 3 single-digit numbers, but they always start at 0. So 0, 1, 2, 3. These are the only digits in the 3 universe, right? So in the universe where we've got base 3, there's only 3 digits. It's 0, 1, and 2. And when you run out of digits, you do the same thing you do in base 10, right? You go to a 1 with a 0. This isn't the number 10 now. I know it looks like it. It's 1, 0. And then you increase from there. You've got 1, 1, and then you've got 1, 2, and then you've again run out of digits in the 1's place. So you increase the digits in the 3's place, what would have been our 10's place, to be 2, 0. And then you have 2, 1, and then you have 2, 2, and this is the biggest two-digit number that exists in base 3. So then we have to exceed 2 digits and we go to 3 digits. It's like hitting 99 in our base system, right? There's no two-digit number bigger than 99. Now we need 3 digits. And the next 3-digit number would look like the number 100. It's 100, and we would keep going. If your book asks for you to like write the first number of digits in a base system, sometimes it doesn't start with a number 0. You can start with a number 0. I think it makes more sense. But sometimes it'll do that too. So if you're looking in the back of the book and they say that and you're like, they started with 1 and I started with 0, it's okay. It doesn't matter. Yeah.
So you said, so like 11 is 1, 1?
We would say it is 1, 1.
1 rod and 1 flat. Like
It would mean, yeah, one long, or rod, one long, and 1 unit. Yeah, so if you had the number, that's a good example. If you had the number 1, 1, and we're in base 3, and we will use the subscript word, 3, some resources would actually write it like this. Your book doesn't, and I'm kind of glad because then the 3 might start to look like a multiplication 3 and that kind of stuff. So this is, I think, probably preferable in my opinion. This would actually mean we have 1 long and 1 unit. And a long in base 3 is worth 3 because we're in base 3. Now imagine if you had, I don't know why we're using ones, but we are. Lots of ones. Imagine we had 3 ones, right? 1, 1, 1, base 3. We would still have 1 of each of them, but now it would be the 1 flat, 1 long, and 1 unit. So the flat would be worth 9 because it's 3 squared. The long would be worth 3. Units are always worth 1. Right? That's what we would have if we sort of like broke the pieces all apart. Does that kind of make sense? Okay. So let's switch gears and not talk about base 3 and let's go to base 7 now, okay? Don't necessarily want this to go away, but do need it to shift over here. So let's move it over. All right, so base 7, we're still starting with 0. And we still go up, but where are we going to stop? Yeah, we're going to stop at 6. We always stop 1 before we get to the base name that we're working in, base 10, right? Base 7, base 3, whatever base we're in. And that's the point when we go to a 2-digit number. So when we get to 7, we don't have a 7, we have a 1, 0. And then we have a 1, 1. And we keep going until we get to 1, 6. And then we have a 2, 0. And what is the biggest 2-digit number that we have in base 7? It'd be 6, 6, right? And then after 6, 6, we'd go to 1, 0, 0. And we'd keep going. Okay, 12 is something different. Why is 12 something different than happened in 0 and 3, base 3 and base 7 and base 8 we even talked about? Yeah. It's already a 2-digit number, right? The number 12 is bigger than our base system. These others that we've looked at are all values that are smaller than our base system. Base 3, base 7, those are smaller than base 10. But base 12 is bigger than base 10. So what we have is we have all of our regular digits that we would have had in base 10, so 0 through 9. But we need a single digit to represent that we are now a 2-digit number, base 10, right? They're not base 10, but 10. And we need a digit for 11. But we need it to be a single digit. So what your textbook does is different for those of you who then have taken maybe contemporary math. In contemporary math, what our books do is that they go to the alphabet and they go A, B, C. I actually prefer that. I think that's much better. It's not what your book does. So we're going to go with what the book does. The book uses T for 10 and E for 11. And if they go to 12, they use W. They don't get any bigger than that, okay? Now, we don't have a single digit 12 in base 12, so we just have a T and an E. That's all we've got. But then after the T and E, we revert back to needing a 2-digit number, just like in the other systems, and we're back at 1, 0 and 1, 1. And once we get to 1, 9, what would happen after 1, 9? 1T, right? we'd do 1T, and then we'd have 1E. That's not a very good E. 1E, and then we'd have 2, 0. So if you think about it like we did on the base 7 one here, where I said, what's my biggest two-digit number? It's 6, 6. What would be my biggest two-digit number in base 12? What do you think, Rayleigh?
I was saying EE.
It is. It's EE, right? That's the biggest single-digit number. So the biggest two-digit number is a duplication of that number, EE. And then after EE, we'd have 1, 0, 0, and so forth. Okay, so just like we did with Babylonians and Mayans and Egyptians, we're going to do the same sorts of things with these sort of random and arbitrary other bases. Some of them are smaller than ours and some of them are bigger than ours, so we're going to do one of each. This question mimics those questions quite well. They say what's before and what's after. And typically speaking, just like with the other numeration systems, one of them is really easy. It's just what you would expect it to be. You're just adding something or taking something away. It's really straightforward. And the other one makes you feel a little uncomfortable. All right? So if you take a look at the 1, 4, and you want to think we're in base 5. So this is the three numbers that we have. They give us the number that's in the middle. It's 1, 4. So this is 1, 4 base 5. They want us to find the number that comes before it and the number that comes after it. Now the number that comes before is the easy one. What would come before 1, 4? 1, 3. That's the easy one here, the one that feels very natural. The problem is that the number that comes after 1, 4 is not 1, 5 because I'm in base 5 and there's no 5s in base 5. It's the uncomfortable one, right? So if I don't have any 5s and I've already hit the number 4, what would come after 1, 4 in base 5? It'd be 2, 0. Okay? And we can do the same thing with base 12. So here's my numbers, 12. Like this. And the number they give us is the middle one, T, 0, 0. Okay? Now, on this one, the more natural one to find is actually the one that comes after. What comes after T00? T01. The number that comes before is more challenging, and I think it's more challenging than the last question that we did too. So I would like to change the question just slightly to have you think about what you do in base 10 when you have a similar style number. Let's say, for instance, you had the number 800. What's the number before 800? You know, 799. But let's think about what happened to get us there. Well, the 8 was a 7, right? And the zeros were the highest value that existed in our base 10 system, right? 9s. So if we think about it from that perspective, we can do the same thing with T00. So the T, much like the 8, needs to be 1 smaller. So what's 1 smaller than T? 9. So this is going to be a 9. And then the largest, right, the zeros became the largest digits in that place value system. So my zeros are going to do the same thing. What's the largest digits in base 12? E's. So these zeros are going to be E. That's not the only way to do it. I'd like to show you one other option just in case you like it any better, okay? So let's think for a minute what would happen if you were trying to explain to a child subtraction where you had something like this. And we're going to talk a lot more about subtraction in section 3.3. But for right now, we're just going to use the basis of what you've done in the past with what's called regrouping, or you may have heard it known as borrowing, okay? So if you were regrouping or borrowing here, what you would have done is you would have taken the 8, you would have made it a 7. I need to make this a little bit bigger. And you would add 10 to the next value, and you would write this as a 10, because when you borrow 10, because you're in base 10, right? And then you would take this 10, and you'd do the same thing. You'd mark it out, and you'd borrow 1 from it, and you would regroup this 10 over here, 0 to become a 10 over here. And then you'd have 10 minus 1 is 9. You have 9 minus nothing now, so this is 9. And then the 7 that comes down, and it's 7. Right? That's what it looks like to do subtraction in our normal base system, or at least it's one of the versions, the one you're probably most familiar with. If I think about our number from the same perspective, I can do the same thing. Hang on, let me turn it back to black. So t 0, 0 minus 1. Well, t is the number 10. So if I borrow from it and I decrease my 10 by 1, it becomes a 9. Make sense? But I'm borrowing in base 12. Borrowing in base 12 means I borrow 12. I don't borrow 10. I'm in base 12, so I'm borrowing 12. Remember, it's like taking my long. My long is 12 long, or my brick, which is a 12 by 12 brick, and it's breaking them apart. When I break that that flat apart, it would break apart into 12 longs. That's what I've got there. Now I've got 12 longs in that category. And now I need to take one of those long pieces, and I need to break it apart. So I take one of the longs away. Now I have 11 of them. That one long is also going to get broken apart, and it's going to become 12 units. Okay? And then I can do the same thing. I can do 12 minus 1. That's 11. But I'd like to write 11 in the right system. Otherwise, I get two-digit numbers in the middle of a problem, which is going to look really weird. I know the letters look weird too, but I need a single-digit number. So 11, which would be written as an E. And then my 12s column is the 11 minus 0. It's also written as an E. And then I have the 9 that comes down, and I have the 9 here. So that's also another way to think about it. And we are going to think about subtraction later anyway, so that's kind of just a foretaste of something we're going to be doing later on. All right, so let's take a look then at what happens when we convert convert the direction of these values. So we're going to convert in two directions. So just like with our Babylonians, Mayans, Egyptians, all of them, we took some of our numbers and turned them into their numbers, and we took some of their numbers and we turned them into our numbers, right? We're going to do the same thing with all these base numbers. We're going to take a base 5 number and make it a base 10 number. Or we're going to take a base 10 number and turn it back into a base 5 number. So we're trying to go both directions on switching these around. So the first one we're going to look at is what happens when we're turning a base whatever else number, base 5, base 12, base 42, whatever it is, into base 10. Okay? So the first thing we're going to do is to put the numbers into expanded form. And let me just show you an example of what I mean by that. Let's say we had the number 321 and it's in base 6. Well, it means that I write 3 and I have 6 squareds. I have a 2 and I have the 6 because I'm in base 6, right? That's what these are coming from. And then I have the number 1 times my 1. This is the units place. So this is the units place. It's worth 1. A long in base 6 is worth 6. And then a flat in base 6 is worth 6 squared. That's what expanded form looks like. You do this with numbers in base 10 as well. You've seen it before at least. Let me write one of those in too just so that you can see that you have in fact seen them. Let's say, for instance, it said 321 and it didn't say anything, so we knew it's base 10. Well, this means 3 times 10 squared. What's 10 squared? It's 100. 3 hundreds. And it's 2 times 10, right? Because it's 20. And it's 1 times 1. So we do this in base 10 all the time. This is the ones place, the tens place, the hundreds place. 100 is 10 squared. And then the second step is to simply multiply out what we have. So if I were doing this one right here with the 321, base 6, I'd actually figure out what is 6 squared. Oh, it's 36, and then I'd multiply it by 3. Oh, what is 2 times 6? Oh, it's 12. Oh, what is 1 times 1? It's 1, and then I'd add them all together. Okay? So that's what this is going to look like, and we're going to do some examples. So we're going to take something that is in base 2. The number looks big because it's a 4-digit number, but it's actually a very small number. It's 1001, base 2. And so we're going to recognize that we have 4 place values, right? So this is the ones place. This is the twos place. This one is 2 squared, and then it's 2 cubed. Why 2s? Because it says base 2. So when I write this in expanded form, I'm going to have the number 1 times 2 cubed. I'm going to have, I know there's zeros, so it's kind of unexciting, but I'm going to write them anyway. The number 0 times 2 squared. Another number 0 times 2, or 2 to the first if you prefer. And then the number 1 times the number 1 at the end. Now, in terms of simplifying this out, these, of course, are 0 because they're multiplied by 0. They don't actually have value for us. But the first one, 1 times 2 cubed, what is 2 cubed?
8.
It's 8. So if 8, 0, and 0, and the last one's 1, so 8 and 1 is the value 9. So again, the picture you should have is you have all these blocks, and you're breaking them all apart. And when they get all the way broken apart, you end up with 9 individual little blocks. That's what happened. We broke them apart. Okay, we're going to do the same thing with the number in base 12, T00. We saw that one earlier when we subtracted 1. So again, this is a 3-digit number. So this is the ones place. This is the 12s place. And this one over here would be 12 squared because it's always powers of whatever base you're working in. So this is the number T. I'll write it as T for the moment. Times 12 squared. Plus the number 0 times 12, or 12 to the first. Plus the number 0 times 1. Now, at some point along the way, we want to remember what T means. T means 10. So what I really have here is 10 times 12 squared. 12 squared is 144. And 10 times 140, well, and then there's a bunch of zeros. I'll put them in. And then 10 times 144 would be 1440, or 1,440. So this is turning a base whatever number into base 10. I'm breaking it apart. It might be a good idea over here for you to sort of make a note to yourself that says that this is a multiplication process. So when you're moving from base whatever into base 10, you will be multiplying. You will be multiplying. So we're going to go the other direction now. We're going to take whatever other the base is that we're in, and we're going to go, we're going to take whatever our number is, and we're going to go back into that other base. So now we're going to take our base 10 number, and we're going to turn it into a base 7, or a base 12, or a base 9, or whatever it is, okay? And when we do this one, if I multiplied before, what do you think I'm going to do now? I'm going to divide. So as I work and turn something into another base, whether it's bigger or smaller, it doesn't matter. But when I take one of my numbers and put it in another base, I'm going to be dividing. So the picture that you want to have in mind is this. You come into the room and you see all those tiny little blocks. Picture them as Legos so we can stick them together and they stick, okay? There's Legos all over the floor. Okay? There's Legos all over the floor, and you want to sort of partition them back into a way that puts them together in these flats and these longs and these blocks, okay? That's what we're doing. We're going to create as many of these different objects as we can so that we have the fewest objects possible. It's kind of like when you take all of your money and you're trying to get all the pennies to become as many nickels as possible and all the nickels to become as many dimes or quarters, right, and many dollar bills. You're trying to have the fewest amount of coins and bills as you can. It's like that, okay? So we have the first one. The number is 11,028, and we're turning it into base 4. Now, we've done this before. So as we do this, you're going to feel like, didn't we kind of do that? We did. We did it with the Babylonians, and we did it with the Mayans when we were writing their numbers out. We did it with something called, I'd call it division scaffolding. So we're going to do this sort of top hat division thing, and it's going to look like that we did before. That said, in order to be able to know what we're going to divide by, we need to know what place values we're using, what system we're in. We're in base 4. So I need to know powers of 4. And I need to write out as many powers of 4 as it takes for me to have too many for 11,000 to go into. Okay? Or too many to go into 11,000, I should say it that way. So you have the ones place and you have the fours place, and then you're at 4 squared. 4 squared, 16. And I have 4 cubed. What's 4 cubed? 64. I'm just going to write the number underneath it so that we can recognize it. And then we have 4 to the 4th. What's 4 to the 4th? 256. Okay, I'm trying to get close to 11,000. That's my goal. Then I have 4 to the 5th. 1,024. We're getting closer. 4 to the 6th. 4,096. And what is 4 to the 7th? 16,000 what, Faith? 384. Okay. And I'm going to stop. How do I know I can stop? It's bigger than 11,000, right? And in fact, if I had recognized that 4,000 was already going to get me close enough, I probably could have stopped a step before. But you need to make sure that you get as far as you need to get. We've definitely gotten as far as we need to get. And we're going to divide going backwards down this list. Biggest value first, right? So it's imagine you're turning as many of your coins into dollars as possible to start with, right? Get as many dollars out of that as possible, and then you've got less to work with. You're taking all the little blocks that are on the floor, and you're creating whatever that, and this is its base 4, right? So you're creating as many of the biggest sized object as you can, okay? So we're going to take 11,028, and we're going to divide by our largest number, which was 4,096. You will need your calculator. Well, I say you don't need, but you probably want your calculator anyway. So if we take this, how many times will 4,096 go into 11,028? It goes in twice. You might have thought that it might have gone in more initially, but it actually goes in twice. What is 2 times 4,096? Yep, 8192, and then we subtract. Okay, so how many times, I'm sorry, what's the subtraction that you get first? $28.36. Okay, and then we go down the list. So going down the list, I've taken care of 4096. Now I need to do 1024. So 1024 will be next. 1024. How many times will 1024 go into 2836? Twice. So I can multiply that one. Okay, that's 2048, and I can subtract. Okay, so what do you get when you subtract 2836 minus 2048? 788. Okay, so I've taken care of dividing by the 1024. Now I'm going to divide by 256. How many 256s are there in 788? It's 3. What's 3 times 256? 768. And if I subtract, what do I get? 20. Now you might feel like, well, I don't need to divide by 64. It won't go in. And in some sense, of course, that's a true statement. But the very fact that it won't go in means it's going to produce a place value holder 0. So we still need to show the division of the step by 64, because that's going to give us this 0 placeholder. It multiplies by 0. Whoops. I still have the 20. Like, it doesn't change the 20. But I need that 0 placeholder in the answer that's going to show up on the right-hand side of this division scaffolding. After I've divided by 64, what will I divide by? 16. How many 16s are there in 20? There's 1. 1 times 16, 16. Subtract and I get 4. Now what will I divide by? The 4. How many 4s are there in 4? 1. Subtract and get a 4. And again, you might think you're done because you get 0, but you're not done until you divide by 1. So I divide by 1. Of course, it doesn't go into 0 any times. I'm still going to have the 0 at the end. But the answer itself is just beautifully right here. That's my answer. I don't even have to go like with the Babylonians and the Mayans. Then we had to turn it into their symbols, right? There's none of that. That's the answer all right there. So we're going to write it out. We have 2, 2, 3, 0, 1, 1, 0.
You don't do commas?
Nope, you don't need a commas. Nope. We put base 4. We want to make sure we put whatever base we're in next to it. If you wanted to put commas, I guess you could, but I've never seen them listed that way before. Okay, so we're going to do another one. Same process, and this will be where we end. We're going to do it quickly, though, okay? So bear with me while I help you to go through this quickly. The number is 99,999, and we're putting it into base 9 where there's no 9s, just because it's fun. That's why we're doing it, okay? So in base 9, we have the 1's place, the 9's place, and then we have 9 squared, which is 81. We have 9 cubed. I think that, 729. I think that's as long as I remember now. How about 9 to the 4th? 6,561. And what's 9 to the 5th? I think it's too big. 59,049. It's not too big, but anything bigger than that clearly will be, right? So if you want to test it, feel free to test 9 to the 6, but it's going to be significantly too large. So my division scaffolding, I'm going to divide 99,999 by 59,049. And it's only going to go in one time. So 59,049. And if we subtract, we get 40,950. And then we'll divide by 65, 61. It goes in 6 times. 6 times 65, 61 is 39,366. I'm hoping all my numbers on my paper are right. If you notice I do something wrong, let me know. The next one we would divide by 729. Oh, I'm sorry, I didn't do the subtraction. 1584. 729 does go into this twice. If I multiply, I get 1458. And I can subtract to give me 126. 81 will go into this one time to subtract. And we get 45. 9 goes into 45 5 times, which is 45. Remainder 0, but I need to divide by 1, which goes in 0 times to give me 0. I know that was really fast. We're doing the same process we did over and over and over again each time. And our solution is the value still over here on the right-hand side. It's 162,150. Base 9. Make sure you write the base. The only time you don't need to write the base down next to it is if it's in base 10. That's the understood one. Okay?